Swayam Prabha. Digital India. Educated India.
Hello everyone. So welcome back to the third lecture of our first module, that is the first week, where we are talking about some basic introduction to the topic of mechanical measurements. In this particular week we are just setting up different initial concepts which we shall be using throughout the duration of these 12 weeks, and that's why we probably are going a bit slowly. That is, I want you to assimilate each of these concepts carefully, and later when need arises you should be able to make proper use of that. In the previous two lectures you have been introduced to a very basic design of a measurement system, where we have seen that a measurement system or the components of the measurement system can be classified into three categories, or any measurement system can be viewed as a combination of three different components or three different parts. One is the sensors or input stage, where there is some kind of interfacing between the physical device and or physical system and the input side of your measurement system. Then there is a signal processing stage, and finally there is an output stage, that is the signal which has been processed in the signal conditioning stage is supplied to some kind of output device through another interface. We have talked about different properties of the measurement system in the previous lecture. We have seen that generally all the properties of a measurement system can be categorized into two categories depending upon their dependence on time. Like any kind of parameter which are dependent on time, or any kind of input parameter which has a time varying nature, it is expected that the corresponding output is also going to be time variant in nature. Now any characteristic of a system is generally referred as some kind of relationship between an input variable and a corresponding output variable, that we can represent either in a mathematical functional form or maybe in a graphical form. Now when we are talking about a system characteristic which is or which relates one time invariant input to another time invariant output, then we call that a static characteristic. And when both inputs and outputs, or maybe one of them, are varying with time, then we call that dynamic characteristic. Dynamic characteristic will be discussed in detail in week number 2, but in the previous lecture we have already seen several kind of static characteristic of system. Some very important one like the property of resolution, sensitivity, linearity, threshold, etc. we have already discussed. Like we have done in the previous lecture also, let us have a little bit of exercise to rehearse all those concepts. Let us take the example of a simple dial gauge, a simple tire gauge I should say. So once we connect this device to the location where we want to get the pressure measurement, we get the reading in the form of rotation of this particular indicator over this particular dial. Now let us try to identify a few of the static characteristics of this particular tire gauge just from observation. Now can you identify the resolution of this? Resolution refers to the smallest possible change in the input required to get a response from the measurement system. I have already received a few queries asking for the differentiation between resolution and threshold, and here I can explain that through the example. Now I repeat, resolution refers to the smallest possible change in the input required to cause a change in the output. So just look at the gauge. There are two scales. Let us look at the one which is on the outer side, which is given in the unit of bar. And now if you look at that, what is the smallest possible value that we can measure? Like here this is 0.5 bar, this is 1 bar, and in between you can clearly see there are 5 divisions. That means each subdivision corresponds 0.1 bar. So if there is a change in the input only by a quantity of 0.1 bar or more, then only the indicator here will show some kind of movement. Like suppose in a particular situation your pressure value is 2 bar, and now if you change the value of pressure from 2 to 2.05, you will not going to get any kind of reading on the scale. It will the indicator or this particular orange colored indicator will continue to be at this particular position only. But only if we make a change of 2.1, then it is going to move to this particular position. So this is what we refer as the resolution. That means we can clearly see that the resolution for this particular tire gauge is 0.1 bar. So we need to cause a change of 0.1 bar, a minimum change of 0.1 bar to get any kind of response from the measurement system. If we look at the other scale, which is given in pound per square inch or so-called PSI, here you can see here we have 10 in one case, 20 here, and we have 1, 2, 3, 4, 5 divisions. So each subdivision here corresponds to 2 PSI. So for the PSI scale the resolution is 2 PSI, whereas for the bar scale it is 0.1 bar. And threshold refers to the smallest possible input that can be measured with the device. Now you can see on the bar side 0.5 is the smallest possible reading that we have. So if the system pressure is something like 0.3 bar, this gauge is of no use, it will not show any kind of reading. So threshold refers to this 0.5 bar, which you can also say it is the minimum value of minimum value shown on this particular scale. But may not be always true. You should consider threshold as the smallest possible input that can be measured. That is the smallest value of the input quantity, whereas resolution is related to the smallest possible change in the input quantity. What about the linearity of the scale? Linearity refers to a linear relationship between input and output. Now if you observe the scale properly, we can say it to be linear if the angle covered by the indicator, say over a range of 0.5 and 1, whatever angle the indicator covers, if that covers the same amount of angle when traveling from say 3.5 to 4, then we can definitely call it to be linear. But just from visual observation it doesn't look like in this particular case, because as we are moving to higher ranges, it seems the angle is increasing a bit, like the angle the indicator is making between 0.5 and 1 and the one that is making between 3.5 and 4 doesn't look to be same. Of course we need to measure it properly. If they are not same, then it is not a linear device, but the linearity is changing as we are moving to higher values. But if this angle is same, then definitely it is also showing a linear nature. And next is sensitivity. Now how can we measure sensitivity of such a device? Sensitivity refers to change in output for a given change in input. So sensitivity for this particular device can be measured by measuring the change or the angle covered by the indicator for a given change in pressure. Like say if we change the system pressure from 1 bar to 2 bar, then how much is the change in the angle of this indicator? Like if we extend this to the center, it will be 1 bar, this will be 2 bar, then this angle is a measure of the deflection the indicator has suffered. Then sensitivity will be given by this deflection divided by the change in the input quantity. Let us take one example. Let us say your device is giving you, or you know that you have connected your device to a location where your pressure is 10, you know that the pressure is 10 psi and corresponding deflection that we can measure from here is 55 degrees. Now we connect the device to another location where again we know the pressure to be equal to 16 psi, and now the indicator showing a deflection of 82 degrees. Now if we assume the scale to be linear, then how can we identify the linearity from these two given set of data? Linearity means output and input will be related by a linear relationship. Like if output is y and input is x, then we can write a straight line equation of the form y equal to mx plus c to relate them, where this m refers to the resolution because this refers to the slope of the calibration curve, and hence it is the resolution. So if we compare the given data with this particular form of equation, then we can clearly say that m can be taken as y2 minus y1 upon x2 minus x1. So for this particular device, your input, that is x, is pressure value, output is the angle of deflection for this indicator. So if we put these values here, y2 refers to 82 degrees and y1 refers to the initial angle, that is 55 degrees. x2 is the second pressure value, which is 16 psi, and the x1 is 10 psi. Here both are in psis. So if we calculate the value, we are going to get the resolution of this particular device to be 4.5 degree per psi. So this way we can calculate the resolution for any device. But what about C? If we put the C values into for any kind of X values, let us compare for the first set, that is 10 psi is equal to this 4.5 degree per psi into I am making mistake again, here y side I have degree only, so I should have written 55 degrees as a y, and x side I have 10 psi plus c. So if we calculate, c comes out to be 55 degree minus 45 degree is equal to 10 degree. Now what this 10 degree refers to? If we say put x equal to 0, then what value of y you are going to get? That definitely is this c, that is 10 degree. Now what that refers to? This is the 0 error. So this 10 degree is a 0 error. Even if we do not provide any kind of input, your scale is showing a 10 degree deflection, and hence once we have idea about this 10 degree 0 error, then any kind of measurement cases we have to consider this, and from the final value then we have to subtract this 10 to get the actual reading for this. So this is one example of how can we calculate any kind of pressure and temperature, or for any other device, any other measurement device, we can calculate the resolution and sensitivity and also the 0 error. Let me take the example of another one, again a very common example of a clinical thermometer. What can we say about this particular device? Again there are two scales, let us talk about the Fahrenheit scale only. So in the Fahrenheit scale, what is your threshold value? That is this 94, this is the minimum value that we can measure from this. How much is the resolution of this particular device? If we compare, let us say this is 96, this is 98, and in between we can clearly see there are 10 divisions, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions. So here each subdivision corresponds to 0.2 degree Fahrenheit, that means it has a resolution of 0.2 degree Fahrenheit. And for a thermometer kind of device, we know that here the operating principle is based upon the volumetric expansion of the thermometric fluid. So the volumetric expansion for any liquid can be related or can be represented as V is equal to V naught into 1 plus alpha into T minus T naught, where T naught is the reference temperature, V naught is the volume of the fluid at that temperature T naught, and alpha is the volume expansion coefficient. Now if we want to calculate the sensitivity for this particular scale, then how can we do that? Let us represent this one in a slightly modified form, 1 plus alpha into theta, where theta refers to the change in temperature from the reference value. So if we differentiate both sides with respect to theta, then what we are going to get? We are going to get it to be alpha into V naught. So what is this dou V dou theta? If we plot a curve where I have the volume of the fluid on one side and change in temperature from the reference value theta on the other side, and if they are represented by a straight line or whatever kind of line, then this is basically a kind of calibration curve or the static characteristic, because here theta or change in temperature is the input, the volume is the output. If we want to talk about the change in volume, say something like V minus V naught, that is change in volume from some initial value V bar, then also we can easily plot the curve the same way by identifying dou v bar dou theta, and that will give you the sensitivity for this particular instrument. Here one important point to observe is this alpha. Now alpha is a property of whatever medium that we are dealing with. So if the medium changes, alpha is also going to change. If alpha is a constant, then sensitivity of the instrument of this thermometer also will remain constant. However, if alpha itself will vary, like commonly such volume expansion coefficients or any other expansion coefficients are functions of temperature, they keep on changing with temperature. So if alpha varies with temperature itself, then the sensitivity of the device also will not remain constant, rather it will keep on changing with temperature or with respect to the input value itself. So this way we can calculate the static characteristic of any device using whatever information that are available. So the range of the device will be from this 94 to 108, that is, it is capable of giving you data over a range of 14 degree Fahrenheit. Now let us move to the next topic of our discussion. This kind of diagram we have already seen for a general measurement system. We know that we initially have a input stage, then we have a signal conditioning stage, and then an output stage. Now in the input stage we have a sensor which provides some kind of interface with the physical system and accordingly acquires some kind of signal which may get transduced depending upon the nature of the input signal. Also we just sometimes compare this with some kind of standard, and the corresponding transduced signal, which is the difference between your measured signal and the corresponding standard signal, reaches the signal conditioning stage. In the signal conditioning stage we may have different kind of components, some just for amplifying the magnitude of this transduced signal, some for converting it to some other kind of signal, etc. This signal conditioning part is individual to the type of instrument that we are dealing with, and so later on we shall be when we talk about any particular instrument, we shall be talking about the corresponding signal conditioning. And whatever output that comes from the signal conditioning stage, the output stage itself provides some kind of interfacing which takes this controlled signal to your output recorder. If we are our objective is to get some kind of control issue, then a part of that output signal can also be passing through the control stage and may provide a feedback to the actual process itself. So this is what a general system may have. But the objective of showing this diagram again is that we can clearly see a general measurement system or any measurement system can have several components involved, and improper functioning of any one of the component can lead to error in the final measurement that we are going to get. That means it is not that just having the a proper sensor or a proper output stage or maybe a proper signal conditioning is sufficient. We have to get all the components perfectly, otherwise we may not get a correct output from our measurement system. Let us take a few examples. Look at this very simple electrical circuit. Here we have a voltage source and 3 resistances. Suppose we want to calculate the current which is flowing through this. Then how much will be the current flowing through this circuit? Using our general electrical knowledge, we know that current will be equal to the potential difference divided by all the 3 resistances, the net resistance, which as the resistors are connected in series in this case, that will be R1 plus R2 plus R3, where R1, R2 and R3 refers to the 3 resistances. Now if we want to get a proper measurement for this current, then actually we have to measure 4 quantities. One is the potential difference or the voltage provided by the source, and 3 resistances. If any one of them is not correct or is has a small amount of error, then the final value of current that we are going to end up with also will have that same amount of error or may even a magnified amount of error. Another example, another very common device which definitely you have seen at your high school physics laboratory, a simple pendulum which is commonly used for in the school level physics, in the school level the school level physics laboratory for measuring the value of acceleration due to gravity. We know that as long as this particular angle is small, generally limited to 1 radian, then we know that the gravitational acceleration can be written as, or I should write g equal to 2 pi root L by g. Here L refers to the length of the thread, g refers to the I am wrong, sorry, on the left hand side we have t, the time period of oscillation, and g is the gravitational acceleration, and t is the time period of oscillation. Or if we rearrange the equation, g comes out to be 4 pi square L upon t square. The mass of the bob of course does not come into this picture. So, to get a proper estimate of this g, we need to have a proper estimate of firstly this L, the length of the thread, and secondly this t, time period of this oscillation. If any one of them is not proper, then final value of g that we are going to end up with, that will also be erroneous. And that means even in such kind of simple configuration, we have every chance of making some kind of error. Let us move to a slightly more complicated relation. This is the diagram of a typical venturimeter or any orifice based flow measuring instrument. You may have already learned this in your fluid mechanics course. If you have not, don't bother about, because later on in our flow measurement module we shall be talking about the working principle for this. But in speaking very briefly, here we have a converging diverging section, like the flow which is coming in through this pipe initially goes through a portion where the cross section area is reducing, and then another section where the cross section area is increasing, and in between we have a small portion of throat where the cross section area is the minimum. And we using some kind of manometer or some other device, we measure the pressure difference between this inlet portion, that is before entering your venturimeter, and this throat section, and that measurement generally gives us a measure of the total flow rate, which can be written as, if m dot refers to the mass flow rate, we can write this as A into CD into power 2 P1 upon RT1 delta P whole to the power half. What the terms refers to here, A refers to the cross section area of the this throat, CD is some kind of constant which generally is supplied by the manufacturer of this venturimeter, P1 and T1 are the pressure and temperature corresponding to this particular location, and delta P is the pressure difference sensed by this manometer. R is the gas constant of the gas for which we are doing this measurement. Here this relation we have written assuming some kind of ideal gas flowing through the channel. Now look at this, how many terms are there which may influence the final value of mass flow rate that you are going to get. One is CD. Of course, it is supplied by manufacturer, but with aging, with repeated use of the device, there may be some change in the value of this constant. Next, the area, we have to measure the area of the throat, we need to measure the pressure and temperature of the inlet section, and also we need to get a measurement of this delta P using this manometer. R is a constant, that is for a given medium, R is a constant, so you do not need to bother about this, but still we have 5 quantities here which we have to measure to get the final measurement of mass flow rate, and if any one of them is not correct, then we may have some error creeping into the final calculation. And if there are several parameters containing error, then their cumulative effect may give a significant amount of deviation in the value, predicted value of this mass flow rate from the actual one. This is what we refer as the measurement error, and that is the topic of discussion in today's lecture, where we are going to get some idea about the general types of errors and also discuss about how to estimate this error. We shall be coming back to this venturimeter example at the end of this lecture to see some sample calculations. Now some common errors. The picture that is shown here, I am sure all of you are aware about this. This is called the parallax error. Like if our objective is to get a measurement of this particular lower elevation, or sorry, the lower surface of this interface, then depending upon our position of eye, we may get different values of measurement. It is a very common kind of error that generally come in our laboratory experiments during observation. Another quite common error, like we are trying to measure the length of some kind of bar using a scale. Very simple situations, we have done this from our nursery class levels, but see what we are doing. While the end of the this one is somewhere here, this particular end should have been at this 0 level, is not it? Should have been aligned to this 0, but here this particular portion have been left out, and so the final value of the length of this bar what we are going to get, that will contain this amount of error. This is again a careless kind of carelessness by the person who is doing this kind of measurement, but a very common one. Another one, see here the interface of the fluid in this pipette is a curved one, and now we are trying to get a measurement. Now which one should we measure? If our objective is to measure the lower one or the upper one, none of them are coinciding with any of the gradual scales that are provided on the device. That means the resolution of the device is not sufficient to give an accurate reading. So if our objective is to get this one, let us erase this. So we know that it is going to lie between this 29 point, okay, sorry, we are starting from the other side. That means we are sure that this reading will be something in between 28.8 and 28.9. But which value should we take? It looks much closer to this 28.9, and we may be just guessing and taking a value of something like 28.88 like that, but that is a pure guess. That is the second decimal point that is coming here. Your device is not at all providing the second decimal point, it is capable of measuring only up to the first decimal point, and whatever we are adding in the form of second or third decimal, that is a pure guesswork. So here the instrument itself is not capable of providing a proper measurement. Another very common error, here we do not have anything on the weighing scale, but still we are having some value shown on the display. What we call this? This is a zero error. No input, but still some output is there. In this case it is showing 0.02 gram. So whatever we are trying to measure, whatever equipment or object that we put on the tray, whatever final prediction that we shall be getting then on the scale, this 0.02 gram needs to be subtracted from there to get the correct reading. So this way there are several sources of error that may be present in any measurement, and or their difference between the true value of any particular quantity which is being provided, or I should say the difference between the true magnitude of a quantity and the value that has been provided as a measuring instrument is called the absolute error. Our objective is always to keep this absolute error to ideally to 0 or at least to minimum, so that we can get the value of the measurement closest to the true magnitude, but that depends on several factors like the instrument related issues, like in this case or in this case, or examples like this where actually it is an error done by the person who is performing the measurement. So absolute error talks about the difference between the true magnitude and measured magnitude. Like suppose we are trying to measure, let us go back to this particular case again. Let us say the true value of the particular bar is L, and what we have measured is L bar. Then this difference between L and L bar is what we are referring to as this absolute error. And sometimes this absolute error is divided by the value of this true magnitude, and that we refer to as the relative error. So relative error is the ratio of absolute error and true value, or in this case it is L minus L bar divided by L, that is 1 upon minus L bar upon L. Generally while selecting this absolute error, we only take the magnitude, that is we shall be putting a mod across this L minus L bar, and then we should not do this particular calculation, we should just stick to this one only. So I repeat, absolute error refers to the difference in magnitude between the true value and measured value of the object which is being subjected to some kind of measurement, and the absolute ratio of absolute error and true value is called the relative error. So if we have any idea about the absolute value of a quantity, then after getting the measured value, we can always calculate the absolute error and the relative error. But generally we do not have any idea about the true magnitude, because if we have any idea about the true magnitude, then there is no point going for a measurement unless we are trying to do some kind of calibration. For a calibration stage, we can definitely take some quantity with the known magnitude, and then by seeing the whatever measurement that the system is returning, we can calculate the absolute error and relative error from there, to mostly to provide or to inform the user about the possible level of error that can be present. But if we are dealing with an unknown quantity, a new quantity, then we do not have any idea about the corresponding absolute and relative errors. The errors can broadly be classified into three categories: gross error, systematic error and random error. Gross errors or blunders are generally associated with the human error, like the parallax that we have seen. Also we here generally refer to some huge blunders. Suppose you have done some calculation and you have measured a length and your measured value is 112.2 centimeter. Now while reporting this, there are several ways you can make careless mistake. Like suppose you have written 121.2 centimeter, so that is wrong. If you have written 11.22 centimeter, that is wrong. And again if you have written 112.2 millimeter, that is also wrong. These are the gross errors. These are impossible to eliminate completely, but we have to be careful while doing any kind of experimental measurement, and generally by repeated experimentation by different experimentalist can sometimes eliminate or at least minimize these gross errors or blunders. Next is the systematic error, which is the most common type of error that can be present. Systematic error again can be of three types: instrumental, environmental and observational. Observational refers to something which is associated with the observation. Parallax, of course I have just mentioned that it can be a type of gross error, but commonly the parallax kind of error we put under observational errors, because this can be eliminated or by measuring the angle at which the observer is seeing, we can do some sort of correction. That is why it is quite often put under this category of observational error. Environmental error are related to different environmental factors, like if there is some kind of measuring instrument which is open to the surrounding, then it can be subjected to all the heat interactions with the surrounding air, the flow of wind, dust particles, etc., which can change the sensitivity of the instrument with or may lead to zero drift or sensitivity drift, which we refer to this environmental error. And the instrumental error, inherent shortcoming of the instrument, like we have already seen an example where the instrument does not have a sufficient resolution to do the measurement, that refers to the inherent shortcoming. There can be some other problem inside the instrument itself. Misuse of the instrument, suppose you are trying to measure some value which is outside the range of the instrument, that is a kind of misuse. And finally is the loading error. Now just take the term for granted for the moment. In the next chapter or in the next week, we shall be discussing about this loading error while talking more about characteristics. So these are the different types of systematic errors which we generally can measure or get an idea about the corresponding magnitude, and then can try to eliminate through calibration. However, random errors are, as the name suggests, are random in nature. Some errors coming from undetermined source or from some completely unexpected source. Systematic errors have always an identifiable source, like the zero drift or sensitivity drift that I am talking about. We can always recalibrate the instrument and get a measure of the corresponding change in sensitivity, or if there is any shift in the zero bias. So we can get the idea about the corresponding source. Like the example of that venturimeter that we have seen, there are 5 different inputs required to calculate the final value of mass flow rate. Then there are 5 ways some kind of systematic error may get introduced. So we can deal with each of them carefully, and it is possible to minimize the error. The systematic error, as I have just mentioned, can be predicted. So it is a deterministic kind of error. It remains the same for all input within range. That means suppose a temperature measuring instrument has gained over a period of time a zero drift of something like 0.5 degrees Celsius, then in any temperature reading that it is going to show, all the values will be containing this. And if we have idea about the corresponding magnitude of zero drift, then what we have to do, let us say we have got a measurement of 11.2 degrees Celsius from the device, then we have to subtract this zero drift from there, and actual reading will be coming out to be 10.7 degrees Celsius. So this way the magnitude of the error should remain the same, or at least always go to the same direction, and hence we can somehow eliminate them. And also they can always be quantified through recalibration, and recalibration generally is the most suitable process of eliminating or taking care of such kind of errors. Random errors, however, are very difficult to track, very difficult to identify the source of such kind of error. They are very unpredictable, often leading to random change in the successive measurement. Like in 3 successive measurement, we can get 3 completely different value going in 3 different alternate directions. Again, to give an example, suppose we know that the length of a device is 1 meter or some bar is 1 meter. Now, if we are dealing with an instrument or trying to measure this length with an instrument which is having a systematic error, we should get the errors all in same direction. Like suppose one device may show 1.03 meter, another measurement may give you 1.02 meter, another may give you 1.04 meter, that is all in the same direction. But for random errors, they can be completely random. You may get a 1.01 meter, you may get another 0.96 meter, you may get another 1.05 meter. Very difficult to compare successive values just from the magnitude, and so very difficult to get an idea about from where the error is coming in. Whereas in this case, we can somehow guess that there probably is a problem with the zero bias, and we have to recalibrate the instrument to eliminate any kind of zero drift which may have appeared. But the random nature of the random errors have made the corresponding analysis more probabilistic in nature, as it is not possible to get a quantified value for them. Rather, we have to go for some kind of statistical treatment. The statistical treatment for random errors we shall be seeing in the next lecture, whereas in this lecture we are focusing more on the systematic errors. So, here I would like to introduce two terms, one is precision, other is accuracy. Both are very common English terms, however, have very different meaning in the context with measurement systems. The term precision refers or deals with the random errors. A device can be said to be precise if the random errors are very small or negligible, whereas the term accuracy generally deals with the systematic errors. A device is accurate means it will have very less systematic errors. Let us take a look at this diagram. Look at the first case. Here several readings have been taken and all are coming in a nice bunch, but that is far away from our actual target, which is supposed to be here. So, we can say that there is hardly any difference between successive readings, and so there is not too much random error. So, the device is precise, but it is definitely not an accurate one. Whereas, look at the second case. Here all are quite close to the desired value, but they are quite a bit scattered. Some on like this one is on one side, this is on the completely other side of the target. So, it is much more accurate compared to the previous case, but it is not precise. That means, the systematic error may be quite low, but there are random errors in successive measurement. Look at the third case. Here all are scattered and none of them or most of them are far away from the actual reading. So, this is neither precise nor accurate, and this is the most desirable situation. Here they are all in a very nice bunch. So, that is precise, random errors are less, and also this bunch is very close to the desired value. So, systematic errors are also less, that is it is accurate as well. So, the term precision deals with the absence of random errors or elimination of random errors, whereas the term accuracy deals with the elimination of systematic errors. While we have seen that systematic errors can be quantified, they are deterministic in nature, and hence we can get some idea about their magnitude. Random errors are very much probabilistic in nature, and so it is not possible to calculate their values. Now, the total error that we get from any kind of measurement is a combination of these two, from where while the systematic part we can get some idea, it is not possible to get any idea about the random one, which makes us very much uncertain about the final value that we have got. Whether unless we have done a large number of simulation, we do not know whether our measurement is precise or accurate or neither or both. And this uncertainty generally allows us to define a new term which is called uncertainty, and this is the term which is more popularly used in correspondence to the measurement errors, and from now onwards, instead of errors, we are going to talk more about uncertainties. We are using this term uncertainty because it may be possible, like suppose we have got a situation somewhat like this in one case. If our true value is not known, we are still not sure whether we have got a correct result or not. Only if we keep on doing several experiments or we use some other device, etc., then we shall be sure that we have got a very precise and accurate measurement. This is the uncertainty which keeps us in some kind of doubt, despite there not being any kind of error in the measurement. That is why instead of using the term error, the term uncertainty is more popular or more common. Let us try to see how we can estimate the systematic errors, and we shall be seeing the method proposed by Klein and McClintock, which is very popular and followed everywhere. Let us say we have an output R, which is a function of several possible inputs x1 to xn. There are n number of inputs that we are supplying to a device, and it is giving an output R. Now, each of these input may have its own error, like say x1 bar is the value of that the instrument actually sensing, which is different from the true value of x1. x1 is the true value, x1 bar is the measured value or inaccurate value or the uncertain value, and the difference between the two is W1, which is the uncertainty involved with the value of x1. That is the value of x1 that we are getting, that is having this amount of uncertainty. Similarly, x2 bar that we are getting from measurement device, that is containing an error W2, and same for everything till xn bar refers to the value of xn that we have got with an uncertainty of Wn. So, each of the values are containing its own uncertainties, and hence what we are going to end up with is not the true value of R, rather with that will be being added with some kind of uncertainty, the WR. Think about the venturimeter situation again. Here this x1, x2, xn may refer to all those 5 variables, that is, if we consider n equal to 5, then x1 may refer to the area, x2 may refer to the CD, x3 may refer to the delta P, etc., and final R is the mass flow rate. So, this is a function that we have got. Now, if all these uncertainties are quite small, then we can we can expand this following the Taylor series with respect to that fixed point x1, x2 up to xn. That is, if we expand this R bar, which is R plus WR following Taylor series, what we are going to get? We are going to get as R plus dou R dou x1 W1 plus to W2 plus this till the nth term plus the second order derivatives. The second order derivatives will be of the form dou 2R dou xi dou xj, where I varies from 1 to n, j also varies from 1 to n, into corresponding omega wi wj plus other term of the order of omega cube. Let us neglect all the terms from second order onwards, and if we neglect all the terms from second order onwards, then we can eliminate R from this side. So, what we are going to end up with is WR is equal to this. This gives us some kind of idea about the error that can be present. Here this WR or dou R dou x1, this is called sensitivity of R to the variable x1. Similarly, dou R dou x2 refers to sensitivity of R to x2. This way, each of these differential refers to the sensitivity of the output to the corresponding input, and W1, W2, etc., the uncertainties present in each of the measurement. Now, once we have got some idea, or we have done this mathematical exercise, then how can we get the maximum possible error that can be coming in? So, each of these terms, the product of sensitivity and corresponding uncertainty, is giving a measure of how much maximum amount of error the concerned variable can import. Like the variable number 2, the maximum amount of error it can import is this particular quantity, the product of corresponding sensitivity and its own uncertainty. Like the variable xn can import this much of error, the product of its sensitivity and its corresponding uncertainty, and from there we get the overall absolute error, which can be considered as the summation of the absolute value of each of these errors, or where each of these contributions, which basically corresponds to the product of the concerned sensitivity and uncertainty. However, in practical measurement, it may very much possible that the error contributed by one particular component gets negated by another one, and so this overall absolute error is going to lead to only very large overestimation. So, a more realistic approach is to go for root sum square approach or RSS approach, where we shall be taking the square of each of these contribution, adding them up, and then finally we shall be taking the root of this particular summation. This is generally the accepted formula for analysis of error. So, whenever we are trying to calculate the error in any kind of final measurement, first we have to calculate the sensitivity of each of the inputs, like this dou r dou x1, dou r dou x2, dou r dou xn. Then we have to multiply each of the sensitivities with corresponding uncertainty, like dou r dou x1 will be multiplied by w1, dou r dou x2 will be multiplied by w2, etc. Then you have to get the square of all these products and then add them together. Finally, this summation we shall be taking the square root of that to get the final root sum square error, or which is conventionally called the uncertainty in the final value of r. A couple of very simple examples, like one case, suppose all the variables are appearing in a product form. So, x1 to the power a1, x2 to the power a2, xn to the power an. Then if we want to calculate, say, uncertain sensitivity dou r dou xi for the ith variable, then basically we are trying to take this to the power a1 to the power a2, xi to the power ai, xn to the power an. So, if we get this product, then what we are going to get, x1 to the power a1, x2 to the power a2 dot ai, xi to the power ai minus 1, xn to the power an, because all the x variables are input quantities and they are independent of each other, and hence we can write this as, if we multiply this as xi and then divide by the same, it is going to lead us to ai into the r itself divided by xi, and finally, if we get the uncertainty, multiply each of them with corresponding w1 whole square, and we are going to lead up to this particular thing. So, this is what we are referring to as the uncertainty in the final value in such a situations where each of them are they are appearing in a multiplication rule. But this is the absolute error. If our objective is to get the relative error, then of course we have to get this WR divided by the true value of R, which often we represent as a percentage one. Another example where they all appear as a summation, then the same we can calculate corresponding uncertainty as AIWI whole square, summation of that whole to the power 0.5. So, let us take a few examples, numerical examples, and try to see the application of this uncertainty analysis. So, we have the resistance of a copper wire related to temperature given by this relation, where R equal to R naught into 1 plus alpha T minus 20. 20 is the reference temperature, and here all the values are given. So, just take a look at the values that are given here. The way here say R naught, the resistance is given as 6 ohm plus minus this quantity. This refers to the uncertainty that is present in the value of this R naught. The plus minus symbol is put to indicate that error can be on the higher side, can be on the lower side also, and this 0.3% refers to the error is actually a percentage of the value, that is 6 ohm itself. That is, the error in this W R naught is actually 0.003 into this 6 ohm, that is 0.018 ohm. That is the error in W. Before proceeding anything, as there is a T minus 20 factor, let us convert that as R equal to R naught into 1 plus alpha into theta, where theta is equal to t minus 20. So, accordingly here this becomes theta equal to 10 plus minus 1 degree Celsius. Look at the way the uncertainty is given for this temperature. Here there is no percentage, just exact value. That means in any temperature reading we may have plus minus 1% error, or sorry, we may have plus minus 1 degree Celsius error. So, from this relation let us try to calculate the sensitivity in the final R. So, dou R naught will be equal to 1 plus alpha theta, dou theta will be equal to alpha R naught, dou alpha will be equal to R naught theta. Now, how much is the uncertainty is present in each of these measurement? Okay, let us first calculate the values. Maybe I do not have a calculator here, but okay, I have noted down the values, so I can use them. So, if we put the values 1 plus what is alpha, that is 0.004 into theta, in this case is 10. So, the sensitivity of R to R naught is coming to be 1.04, and for this theta it is coming to be alpha is again 0.004 into R naught is 6, so 0.024, and R naught into theta for with respect to alpha, it is 6 into 10, that is 60. I am not writing the units, but each of them has its own unit. Like in the first case it is unitless, both numerator and denominator are the same quantity, but in the second case like this one, what should be the unit? Numerator is in ohm, denominator is in degree Celsius. So, the corresponding sensitivity is ohm per degree Celsius, and the same way we can get for the third one also. Now, here W corresponding to R naught is given as 0.003, we calculated earlier also, to be equal to 0.018. W corresponding to theta is equal to 1, because it is absolute value that is given. W corresponding to alpha is given as 0.01, that is 1% of the value, that is 0.004. So, it is coming to be 4 into 10 to the power minus 5. It is an extremely small value, and we should write their units also. So, it will be in ohm, this will be in degree Celsius, and this will be in per degree Celsius. Now, how much should be the contribution from each of them? We have to multiply each of the component sensitivities, the corresponding uncertainties, then get the square, and that will give us the final value. So, final WR will be equal to the sensitivity with respect to R naught into WR naught whole square of this plus dou R dou theta W theta whole square of this plus dou R dou alpha W alpha whole square of this to the power 0.5, and by putting the numbers you are going to get whatever is the final value of uncertainty, and if we do it we are going to get 0.0305 ohm. But this is the absolute uncertainty, and if our interest is to get the actual uncertainty, or sorry, relative uncertainty, then we have to get the true value of R. How to get the true value of R? There we have to use the values that is given, like true value of R will be equal to, when we put the value of R naught that is given, that is 6 into 1 plus 0.004, that is for alpha, into theta, that is in 10. This is often referred to as a nominal value. So, it will be 6 into 1.04, and whatever value you are going to get is say 6.24 ohm. So, while the actual measurement should be 6.24 ohm, we are going to get 0.0305 ohm uncertainty in that, which is about 0.49%, which is very, very small. This way you can calculate uncertainty. Just another example for you to check. Here we have two resistors R and RS connected in series. Voltage drop across each resistor are given by E and ES, and then RS values also the uncertainty is given. So, we can say, so we have one register here, we have another register here, and we are having say this much of voltage drop E here and this much of voltage drop ES here. A current I is flowing through this. So, if you have to calculate the power that is being dissipated in the resistor R, the corresponding power will be equal to E into I. Now, we know that I is equal to E by R and again ES upon RS. So, if we put it back here, it will be E into ES upon RS, and or if I write, so we have a relationship between the desired quantity which we want to calculate and the three values for whose values are measured and uncertainties are given, and this is the corresponding power error that you will be getting 20.18 watt or 1.11% uncertainty. I request you to do the calculation. I will leave you with a couple of problem exercises which you please try to do till the next lecture. In one case, I have given you a resistor which has a stated voltage of 10 ohm plus with an uncertainty of 1%. We have to calculate the power dissipated by the resistor on the application of a voltage across it. Both value and uncertainty in corresponding voltage and current are given. Now, power we can calculate in two ways. We can calculate power as an I square R term. We can also calculate power as EI term. In one case, like in the first case, we have to measure only the current. In the second case, we have to measure current and voltage both. Try to solve for both the cases and see which one is giving how much of uncertainty. And the final problem, where the problem of venturimeter that I mentioned earlier, the relation is given and all the 5 parameters with their values and uncertainty is given. Try to calculate again the final uncertainty, but another thing, you please try to check from here which one is going to give you the highest contribution among all the 5. In the next lecture, I shall be coming back to this problem to see how can we select the instrument. Like in this case, if their uncertainties are different, you may get an idea about which process to follow. After getting your answer, I can proceed with this, and same in this problem, try to see the product of sensitivity and uncertainty for each of the components and compare those values to see which one is having the largest contribution in the overall uncertainty. So, I am leaving with you with this. In today we have discussed about different possible errors and uncertainties present in measurement. I have talked about systematic and random errors, and then uncertainty analysis in terms of systematic errors. In the next lecture, which is going to the last one in module 1, we shall be talking about the random errors and corresponding statistical treatment should say. So, thanks for your attention. Please solve those two exercise problems. Try to solve each of them that we have discussed, so that before you start the next lecture, you have a good idea about how to deal with the systematic errors. Thank you.